Okay, it's showtime, folks. We got the Algebra 3-4 Chapter 5 video study guide. And my example problems this time are going to be from the Chapter 5 practice exam. This one's going to be a little different because looking through the Chapter 5 practice exam, a lot of the problems, there are like different parts, like parts A through D or whatever they are. They're broken apart. And the only issue with that is, you know how normally I'll go through a set of notes, and then I'll go through example problems that correspond with those notes. Unfortunately, these problems merge so much together, and you'll see all the examples, but they merge so well with each other that you have to kind of teach everything first before you do the problem. So this time I'm going to talk through all the notes first. Maybe I'll give some examples along the way. But I'm going to talk through the notes through that slideshow, and then I'll go through all 8 example problems. And hopefully they're extensive enough that, not exactly the example problems are extensive enough, but everything that I talk about kind of gets covered in a way where no matter what you're asked on an exam, you still benefit. Okay, I'm going to start with the idea of quadratic functions. Now go with the screen. Go with me on the screen here. Quadratic functions are second degree polynomials. What I mean by that is they have an x squared term. So you take a look here. There's an x squared. And in this form here, if you distribute this, if you FOIL it out, you also get an x squared there as well. Okay, they are parabolic in nature. No 3 points are collinear. So they are not linear at all. Everywhere it is a smooth curve the whole way through, no angles. And they always have what's called a vertex. So you'll take a look right there, that circle. That is a vertex, and it is a point where your parabola continually goes up on both sides of it or back down. And your vertex is also a point where a line can be drawn straight down the middle called the axis of symmetry, where you can reflect on either side of that thing, meaning these are mirror images of one another, as opposed to probably most other graphs. And there's that specific point, which makes that happen. There are 2 equation forms that we really look at when we're talking about a quadratic function. One is called standard equation, and it comes in this form. You have a quadratic term with a coefficient of a that can't be 0, otherwise it's not quadratic, multiplied by your x squared, and perhaps there's a bx and a c also being added to it, your bx being your linear term, and your c being your constant term. Now these don't have to be there. If you have 0 for b and c, that's okay. This is still a quadratic. And 1 might not exist like that or like that. Regardless, these are always still quadratic functions. Now, if b doesn't exist, you're actually looking at a graph that has no horizontal shift. Like, for instance, this guy over here. This is y equals x squared plus some c value. There's no b value. It doesn't shift to the left or right for your vertex. And if your c value isn't there, that would mean it's 0. And this still refers to your y-intercept. So if your c value is 0, then your y-intercept's at the origin. And I want you to keep in mind your vertex and your y-intercept, like here, and like here, aren't always at the same place. In this case, yes, your y-intercept and your vertex are both the same thing. But don't make any mistake thinking that your y-intercept is just your vertex. Okay, that's one way to express polynomials, and like I said, all the practice problems are at the end. So there's this way, and to get to vertex form, you can do a couple things. You can either find the vertex or do what's called completing the square. And when we do that, you'll get a good idea of that. And you get to what's called vertex form, or the vertex equation for a quadratic function, which has the same a value as this guy, by the way, and this is called a stretch factor. And we'll get into that on the next slide here. But a stretch factor has a lot to do with how your graph ends up looking. It's kind of like slope, only I don't want to call it slope to imply it has a constant rate. And then you have these 2 values, h and k, which are the location of your vertex. So if you've been attuned to when we did absolute values, it's the same idea. And remember, you subtract h, but you add k. So take a look at what your h value is exactly, specifically, and not don't. So if this is x plus 2, that's x minus negative 2. That's x minus h. So your h would be negative 2 in that case. Here's another way of looking at your vertex. That looks kind of weird, so let me rewrite that. It'll still look weird. Negative b over 2a. We've discussed that at great length before. Okay. What you'll do to find your vertex, besides the point being hk, if you take this standard equation form right here, and you take the opposite of this value and divide it by 2 times this value, you will find the x value for where your vertex is. So this could be your negative b over 2a location. And then your f of x value, if you plug that in, you'll find your y value that relates to it. So if this is negative b over 2a here, down here is f of negative b over 2a, and there's your vertex. Down at the bottom here, we're looking at 3 different graphs, and all these graphs just show unique things, not that one means something and one means something else, whatever. But in this graph, I'm going to go ahead and look at that vertex equation again, just so you have a good look at what I'm going to talk about here. You may be given a graph, and you might be asked to write an equation. Whether it's in vertex form or standard form, it's great to use vertex form first because you have here a y, an x, an h, and a k. If you take a look at it here. If you know your vertex, h and k, and you know another point on your graph, doesn't matter where it is, as long as it crossed through a distinctive point, like xy right here, you can actually plug in all those values and find your a value. And then when you do, you rewrite your equation so that it's y equals whatever a was. Let's say it was 2, like y equals 2 times x, I don't know, maybe this is minus 1 squared plus 4, something like that. Regardless, that's an example of what you do. You find out what your a value is, and you put it back into there, and there's your final equation. And if they wanted standard form, by the way, I forgot to say this, if you want to go from vertex form to standard form, you have to distribute the square. Well, not distribute. You have to, FOIL it and combine like terms. And then you can get into standard form here. So I want you to keep in mind your b value has very little to do with what you can see on a graph, except for right here when you talk about negative b over 2a. It's good use for completing the square. The rest of these values, a, c, h, and k, have very much to do with your graph, literally. The only other things I wanted to say about these graphs are where are they crossing their x-axes. You see right here and here, crosses the x-axis twice. That means there are 2 real solutions, or they also call them zeros or roots. Okay, so if you have an equation in this form or in this form, and you're trying to find what your value of x is when y is equal to 0, the benefit to quadratic functions is there's this whole square root process here, or the way that you factor, where you can get more than one solution, as such seen right here. And you can possibly get as many as 2 solutions. 2 real solutions, I should say. Another example is when you set it equal to 0, and it's kind of strange. You only get 1 real solution. Doesn't happen very often with quadratics unless your vertex is on the x-intercept. That's the only possible place. The only possible place for a parabola to touch the x-intercept only once. Because you have to remember, if it was down here, anywhere, this has an axis of symmetry down here, so it's going to cross at 2 different places. And if it was any lower, it wouldn't touch it at all. So this only happens when vertex is on x-intercept. And finally, here's an example where your parabola never crosses the x-axis, where you have no real solutions, or zeros, or roots. Right here, it starts either above the x-intercept and it keeps going up, or it starts below the x-intercept here and keeps going down. And we'll see all those. Hopefully, I do believe in this practice test you see all those kinds of graphs. Okay, let's talk about how to graph these guys, and then maybe we can go over some of the we'll go over some of the problems later on here and see if they make sense. I'll try and explain this as best as possible without going way over your head on it. Now, this is a picture on my whiteboard that I had a student take a picture of, and this has been up here for quite a while, but it's now taken down, and I want you to kind of get a pattern and relationship between what's happening. We call this a shorthand approach to graphing quadratic functions. Now, I don't want you to think of this as a shortcut, like as in, oh, you could just do this and you're good, you don't have to understand everything. This has pretty much a great deal of explanation behind it, actually. Let's take a look at a parent graph here. And by parent graph, I mean this is 1x squared plus 0. Looks like I'm writing on a whiteboard. Okay. From here, you'll kind of see what that a value, what we call the stretch factor, what this guy does to your graphs. All right. Now, all of these values right here, these coordinate points, yeah, this says 0, 0, 0, 0. I'm not going to refer to this exactly as the origin. What I'm going to call this value right here is how far I am from my vertex. So right here, this will be assuming that you are on your vertex. Okay? Okay. So if you graphed this, however, y equals 1x squared, you plug in 0 for x, you get 0 for y. 1 for x, you get 1 for y. 2 for x, 4 for y, etc. 1 squared, 2 squared, 3 squared, and so on. And actually, if we call this negative 1, negative 2, etc., you'd still get the same values. You will basically reflect across your axis of symmetry when you do that to get those other points, and we'll talk about that as we graph them. But what happens when you change this number? From a stretch factor of 1 to a stretch factor of 2, for instance. How do your y values change compared to your x? Well, here's what happens. Order of operations says that we do exponentiation before we do multiplication. In other words, I am still going to square x before I multiply by whatever my stretch factor is. In this case, you multiply by 1, no change in it. Now I'm going to multiply by 2. So when I go from 0 to 6 on my x, because these are our independent values, excuse me, and we do not, and you can change them to whatever you want, but the point is, as you grow by 1, first of all, this is not a constant slope. First we went up 1, then up 4, then up 9, then up 16, etc. It's not 1, then 2, then 3, then 4. Okay. But here we went up 1 squared, 2 squared, 3 squared, 4 squared. This time we're going to go up 1 squared times 2. Remember, 2 is just the number 1 times 2. Here, let's see if this is a smaller. That'll work. Here, instead of going up 2, or going over 2 up 4, now we're going to go over 2 up 8. 8 is 4 times 2. Here, instead of going over 3 up 9, we'll go over 3 up 18. 18 is 9 times 2. You start to get the picture here. Instead of 416, you'll go 416 times 2, which is 32. So what's happening is this 2, or this 3, as you'll see as I start to explain it more, this stretch factor says how much I vertically stretch my graph. Okay? And how far away these points go from your vertex than they normally would. So when I call this guy a parent graph, all I mean is that by default, you kind of make sense of the fact that when you go over 1, you'd go up 1. Whenever you go up over 2, you'd go up 4, etc., etc. So I boxed this right here because what I kind of tell people whenever I talk about this is remember the numbers 1, 1, 2, 4. So you kind of have something in mind because essentially you normally don't get axes, a set of axes that are so big that you can plot 36 points above your vertex anyway. This is normally enough. And, well, hey, if you have to multiply it by 2 or 3, you'll see how much bigger that number becomes. So this is kind of enough points here. You go over 1, you go up 1, you go over 2, you go up 4. However, in the event that you have a stretch factor, I almost thought I was going to erase the whiteboard portion. That was kind of funny. If in the event that you have a stretch factor applied, like 2, let's try 3 this time. Now, instead of going up 1, you're going to go up 1 times 3. Well, 1 times 3 is 3. That's where we're getting that number. You go over 2, you'll go up 4 times 3. And 4 times 3 is 12, etc. Now, this should make enough sense. I'm literally doing the same math as here, but if you can kind of apply 1, 1, 2, 4, and instead just think about what your stretch factor is, then you'll be in good shape the whole way, because this isn't so much just about coming from the origin. Remember, this comes from any vertex. I'll give you another example. Because I honestly don't know how many examples you'll get in this practice test. So let's do y equals 2 times x minus 3 squared plus 5. Okay. Now your vertex this time, let's plug in xy. Your vertex this time is at the point 3, 5. Okay. A positive stretch factor does mean that your graph will go up instead of down. Now, why is this 3, 5, you ask? Or better yet, because people always ask this, why are we subtracting 3 instead of adding it like we had 5? Because we're trying to find a value for x that will that will minimize our y value. For instance, when I plug in 3, I get 3 minus 3, which is 0. 0 squared is 0. 0 times 2 is 0, and 0 plus 5 equals 5. So I get that point. But the truth behind this is, no matter what number I plug in besides 3, I will always get a number greater than 5. 2 minus 3 is negative 1, okay? Negative 1 squared is 1. 1 times 2 is 2. 2 plus 5 is 7. So there's a point right here. If I plug in 2, I probably should have went the other way. I plug in 2, I get 7. Okay? And if I plugged in 4, this is really the one I should have plugged in. If I plug in 4, I also get 7. 4 minus 3 is 1, etc. Plug in 5, try the same thing. 5 minus 3 is 2. 2 squared is 4. 4 times 2 is 8. 8 plus 5 is 13. And I'll plug in one more point to really get my point across. 6 minus 3, 3 squared is 9, times 2 is 18, plus 5 is 23. So here are a set of points. Now, whenever I do this stuff right here, I want you to notice that this is my distance, my vertical displacement from my vertex. So this is saying, how far away are these numbers from my vertex? Well, 4 is really just 1 unit away. And when I went over 1 from my vertex, I went up from 5 to 7. I went up 2. 5 is 2 units away from my vertex. When I go over 2, I went up 5. And 13, I went up 8. When I go over 3 from my vertex, I went up 18. These numbers, remember this is 0 away from the vertex, by the way, 0 and 0. These numbers, 0, 1, 2, 3, 0, 2, 8, 18, both look the same no matter where I am. So again, it doesn't matter if your equation looks completely different right here. This is still how far away are you from your vertex. So when I do a couple of the practice problems that we have, I'll keep this in mind when I talk about it. When you're dealing with fractions, it's the same idea. When you go over 1, instead of going up 1, we're going to go up 1 times 1 half. Half of 1 is 1 half. Instead of going over 2 up 4, we'll go up 4 times 1 half, which is 2, etc. Now, what I circled and showed right here is that if you don't want to get integer answers, or integer, displacement, go over the same amount as your denominator. Because then you're going to divide by a number that's divisible. You're going to have a number that's divisible by 2. Remember, you're taking half of those numbers. So maybe go over 2 instead of over 1. You don't have to land on a fraction. Same with 1/3. I plug in 1/3. Instead of going over 1 and over 2, I'm going to go over 3 first. And then I'm going to go up 1/3 of 9. Remember, this is 9 times 1/3. Instead of going over 4 and over 5, I'll go over 6, and I'll go up 1/3 of 36, which is 12. Okay, so those are some points you can plot. And the other points you can plot, remember, I want you to keep this in mind. Negative x squared is the same thing as when you go over this way. I'm sorry, I put that wrong. When you go over this way, instead you multiply by a negative number, so you'd go downward. So a positive stretch factor goes upward, and a negative stretch factor goes downward. Okay, I want to talk about word problems. Now I'm shifting gears here. Word problems are actually kind of nice. I really do like them, despite the fact that a lot of people tend not to. Maybe they think, well, they're wordy. Well, yeah, they are wordy. But the really good thing about it is that your answers tend to make sense when you do word problems. The best thing about these word problems is you don't actually have to set up an equation, at least for the most part. There are instances like those lake problems with the fence and such where, yeah, an equation comes into play. But most of them say something about, well, there's a model that's made for you, and you just have to understand some critical points. Some critical points happen to be like your y-intercept, your possible x-intercepts, and your vertex. Those are most often the three sets of critical points that'll matter the most for word problems. Okay, like linear models, it's important to understand what the question is asking. Super important. The first thing you want to look for is, what is, like, what am I trying to solve for? Right? Am I trying to plug it in for x and y? I don't know. This will help you determine what information you don't know, because these, like I said, these become your unknowns. I want you to be wary of their units of measurement. So if something's in dollars, you must answer in dollars, unless they ask for cents, etc. And as I said, this lets you know what variables to solve for and what values to substitute in. So if they ask for some certain word problem, like this one here, like throwing a ball into the air, normally throwing the ball into the air, your x values tend to be the time it takes, so your time is maybe in seconds, and then your range, your y values, are probably feet or something like that. So if it's asking how long will it take before the ball hits the ground, you know you're solving for a value for x when y is equal to 0, etc. You want to make sure that you know what values to substitute. So this is what I was talking about before I went to the actual ball problem. My recommendation to you is that because all quadratic word problems really do have this natural domain and range, meaning if they are those projectile problems, like a ball being thrown or something and it comes and lands, there is this natural idea that, well, normally there are restrictions on your x and y values. Like if I have this set of axes right here, I'm probably not looking below, if this is a ball being thrown up in the air, I'm probably not looking below the ground here and here. You're probably looking at only points that are above the ground, so to speak. And, who knows what kind of problem this is. Maybe this is a problem where you're trying to, deal something in terms of a business, and you're trying to model this, and you're trying to say, well, this is over a certain period of time, so I need to know when time began. And maybe time begins right there, so you don't look to the left over here because you know that that's nothing. We're only going to look to the right. Okay? So there are a lot of different instances where you want to say, I know what the question's asking, and I understand that there's a natural domain and range happening. So like I said with the ball, the time it takes for the ball's release to its impact with the ground, and its range might be from ground level to the maximum height of the ball. So your range meaning how low can it get, how high can it get. And that's good to know. Okay, shifting gears again. I want to start talking about things involving expressions. And by that I mean I'm not yet talking about solving for quadratic functions. In this case, I want to talk about how to factor. All right, and there are three different ways, and I don't have very many examples on this practice exam to do it with, so maybe I'll do these with you. Okay, explain my examples that I did, and I'll do it down below. Factoring is the opposite of distribution, so there are benefits to doing distribution sometimes. Like I said, going from vertex form to standard form, or other things. But factoring is a way of simplifying expressions. It's an appreciable way to help simplify expressions. And there's good use to it to clean up some problems, all depending on what you're talking about. Normally the benefit to distribution is if you want to combine like terms, and perhaps something can be factorable as a result. Otherwise, factoring is the nice way to put things. And, oh, by the way, the opposite of factoring is distribution. So if you ever wondered if you factored correctly, go ahead and distribute your terms back in and see if you did it right. So there are three different ways that we're kind of doing factoring here. And one way is talking about common factors, which means among any or all terms, you find a common value / letter multiple that you can divide out of them. And by letter, I mean a variable like x. So you have this example here, 6x cubed minus 24x squared plus 15x. You want to find a number that is a multiple of 6, negative 24, and 15. In this case, it was 3. And then you want to find perhaps a variable that's a multiple of all of these three guys, which is x. And you can factor those two out. And you're left with 2x squared minus 8x plus 5. on the inside after you divide out 3x. Okay. Another way of factoring is if you have no common factors. And by that I mean this x squared is 1x squared, which means you can't factor out a number. And then you have a constant term, which means you don't have an x value. So no common factors, so we can't go for a greatest common factor. By the way, I should label that GCF for greatest common factor. There is one, but it's not in the sense that it's just one number here. What we're going to do is kind of take a look at this diamond example here. And I don't know why they call it a diamond when you draw an X. Some people go for diamond like that, which is just fine. All this diamond is a visual representation of asking what two numbers multiply to something and add to something else. And we use the letters C and B to express or to represent this C and B right here. We want to find two values that add to B and multiply to C. And I'll show an example. First, by using this, I will go backwards by distributing to show that I can get to this and kind of say exactly what's happening as we go on. So let's go and take a look at that example here. We get, x plus 8 times x minus 4. Now, people can talk about FOIL and all that, and I'll get into that. I'll get to the foiling step. But before that, I want to show you that this x value gets multiplied by this quantity here, and this 8 value also gets multiplied by this quantity here. So I'm going to write this out instead as x times quantity x minus 4 plus 8 times the quantity x minus 4. And this is an important step for me when I do this factoring by grouping step over here in this third example that we do later. Now comes distribution. You can distribute the x with the x, and the x with the negative 4. You get x squared minus 4x. This is 8 with the x and 8 with the negative 4 plus 8x minus 32. Plus 8x minus 32. Okay. This is normally where you say FOIL. FOIL is first times outside. First times outside. Times inside times last. That is these two inside guys and these two last guys right here. So I put an intermediate step, again, for good reason, and hopefully you'll see it later. So here's your FOIL. After that, what happens is these two terms combine. Negative 4x and 8x, or these two, the outside and the inside terms, will always get this combination of, hey, these can merge down to one number. In this case, they become 4x. So the idea that you want to keep in mind here is that this 4x, remember, it was originally in this form. This 4 is your b value. Now, your b value was a sum of two values, negative 4 and 8. Okay? Negative 4 plus 8 combined to this number. That's why we call it a sum. We say what two numbers, again, when I was writing up here, add to b. Excuse me. And we also want to find out which two numbers multiply to c. Because if you noticed, your last numbers here were 8 times negative 4. They were your two last numbers here, and these happen to be the product in the end right here. Okay, although you didn't feel the pause, you might have seen the time jump like 10 minutes. I had the hiccups for a while, and I just did every trick in the book. I ended up going onto a website where there was a pop-up screamer and scared myself. And they're gone, I think. We'll see if they come back. Okay. Where was I on this problem? So what we were doing was we were distributing this to kind of show where everything came from. And the whole idea was to make sure we saw, okay, your product is were your last two numbers here. And your sum were these two numbers here. Okay. One other thing that I might want to keep in mind as I talk about this is I want to say that these two x's, these are really one x. And that's a key value, or that's a key idea when it comes to saying what negative 4 is being multiplied by. It's not just x, it's being multiplied by 1. And 8 is also being, I want to get rid of that. Okay. And 8 is also being multiplied by 1x here. So will be key for the next thing we talk about. Anyway, so if we were to go backwards, let's go backwards here. We have x squared plus 4x minus 32. And we want to find what two numbers multiply to negative 32 and add to 4. So with negative 32 here, an important thing that you have to know is this number is negative. And because this number is negative, that means that when you list factors, one of your numbers will be positive, the other will be negative. Okay? Now, the positive number will be bigger because when you're adding these two, the positive and negative up together, you're getting a positive result. So when I list factors of negative 32, I want to make sure that I list the bigger number, the positive number, as the bigger number. So you take a look at these guys right here. And that's it. If I listed negative 8 and 4, I know I'm not going to get positive 4 as an answer. So you might as well only list the ones that'll end up getting you a positive result. Anyway, you add these up. This gives you 31. This gives you 14. This gives you 4. Oh, there it is. We're good. Your two numbers are 8 and negative 4. Now, ordinarily, the next steps aren't necessarily necessary, so I won't do them here. From right here, you can say that's x plus 8 times x minus 4. Whenever you're running into a scenario that's x squared plus bx plus c, that is to say that there is a 1 in front of this coefficient right here. Now, if there's not a 1 in front of your coefficient, like this scenario right here, if you have an actual other value, and with this value, you can't find a common factor of a, so you can't get it to 1. Now you kind of have something a little more different and a lot more difficult to deal with. So I want to keep the stuff on the left to give you an example of what I was talking about before. And I'll give you two different ways to do this here. Okay. We have to factor 3x squared plus 13x plus 10. Okay. When we go to this diamond, you can do this one of two ways. And I'll try and explain both and see if both of them make sense. First way I'm going to do is multiply this 3 value with this 10, and I'll get 30. If you look up top here, when I showed this diamond example here, you are always doing your a value times your c value up here. It's not just your c value, even though I wrote that before. The difference is in the x squared plus bx plus c scenario, this is also true, but our a value was 1, so 1 times c was just c. That's why we had that. So you're always really multiplying it by a. You're finding your numbers that multiply to that still add to your b value, 13. You work through it, and I work through it some more. You get 10 and 13, or 10 and 3, or 3 and 10. In fact, it's probably better that I write 3 and 10 to get this thing in proper order. You'll kind of see why here. What I'm going to do is rewrite it into this expression right here so that I have my sum. This is a very big reason why I have this step right here, the FOIL step. I'm going to rewrite this so I have my sum written here. And then I'll do another step that's called factoring by grouping. Basically what happens, you look at these two terms and these two terms, and they will always share, like this pair shares a common factor with one another. And if you look above here, when we did distribution, this is why this step is so crucial. This step shows you that this value, x, gets multiplied by this quantity, and this value, 8, gets multiplied by this quantity. So if this is even factorable, then that means that they each share a common factor with each other, and we needed to break it down to this. So we need to start breaking this apart because this was distributed from something else. So if I factor out a 3x here, I get x plus 1. And if I factor out a 10 here, I also get x plus 1. It is not of coincidence that I got the same number here and here, because this should have been a common factor. Anyway, I pull that out. X plus 1 is now a common factor in those two terms. So that is x plus 1 there. And what's left in the other guys, if I pulled out an x plus 1 from this term, I'm left with a 3x. If I pull out an x plus 1 with this term, I'm left with a 10. So your final solution is 3x plus 10 times x plus 1. And you also get that up there. Okay, simplifying radicals. This is something that's going to be taken care of a little bit more when you do quadratic formula or completing the square, which is why I wanted to get through it first. Okay, here are a few properties that would be good to know. Okay, the root of a product, like this guy right here, is equivalent to the product of two roots. In other words, if you have a number and you can factor it into two numbers, other than like itself in one, like the number 8. If you can factor 8 into 4 times 2, you can break 4 times 2 into the square root of 4 times the square root of 2. Okay, the idea behind simplifying radicals is you want to extract perfect squares. You can see it right here. To simplify radicals means to find perfect square factors that you can get out of the root. Okay? Now, the same thing goes for fractions. The root of a fraction is equivalent to the fraction of two roots. Now, you have to understand when we do all these problems, we are talking about square roots. So domain still matters here. I can't have negative roots. And oh, by the way, in the denominator, in this fraction example, you wouldn't have it anyway, but your y value can't be 0. So yeah, y can't be 0 in the fraction example. Okay, again, to simplify these things means to get perfect roots out. So whenever you do these examples here, you really want to make sure that you are trying to divide by a perfect square wherever you can find it. Use any of those numbers. Can you divide out of it? Okay, cool. If you can, move on. I'll give one example down here just in case I don't run into these as I go on. Take the square root of 2. Take the square root of 72. Square root of 72 you can do a lot of different ways. One way that I'm going to do is try and find the biggest perfect square I can get out of this. 4 divides into 72. So does 9. 16 does not. 25 does not. 36 also does. And 36 actually is exactly half of 72. So this is the biggest number, perfect square I can get out of it. The square root of 36 is 6. So I end up with 6 times the square root of 2. Another way of saying this is 6 root 2. Well, what if I didn't divide out 36? What if I divided out 9? If I divide out 9, the square root of 72 is the square root of 9 times the square root of 8. And that becomes 3 root 8. But the thing is, I can still simplify the square root of 8. Square root of 8 is 3 times the square root of 4 times the square root of 2. And the square root of 4 is 2. So 3 times 2 times root 2, that's 6 root 2. You still get the same answer, but with a little more work. Okay, let's do this one more time. Let's say you didn't know that 9 was a perfect square and you divided out of 4. That's square root of 4 times square root of, oh, help me out here, 13, not 13. 17. That's not right. 18. I need a calculator. Square root of 4 times square root of 18. So square root of 72 equals 2 times the square root of 18. But the square root of 18, oh, by the way, can break apart into the square root of 9 times the square root of 2. Now, if you did not know that one, if you couldn't find a perfect square out of that, maybe you end up getting this, square root of 6 times square root of 3. Well, the square root of 6, the square root of 6 is the square root of 2 times the square root of 3 times the square root of 3. Here's where your third property comes in. Should all else fail, break down original point value to prime factors and join pairs of identical roots, like the square root of a times the square root of a equals a. Well, the square root of 3 times the square root of 3 equals 3. So this is 2 times 3 times root 2, which is still 6 root 2. Okay? So those are your different ways of talking about those things and making sure that you can, get the right answer out. You should always get 6 root 2 for the square root of 72. Okay, and this might be the finally. Finally, solving quadratic equations. Quadratic equations, I'll go and read this. Quadratic equations are unique compared to linear equations because in a linear equation, you can potentially solve for x just by getting it by itself. You can subtract any things over, combine like terms, and divide by a number, and boom, it's done. Okay, X cannot be isolated, however, in a simple way when there exists a quadratic, linear, and constant term. In other words, all these guys don't equal 0. Take, for instance, one of these guys over here. X squared plus 4x minus 32. Let's say we wanted to solve for x. Somebody might say, oh, by the way, let's say it's equal to 0. Because to solve for x, you need an equation for it. Okay, let's say you want to solve for x. Most people say, okay, get it by itself. So you add 32 over, and you get x squared plus 4x. You're like, okay, solve for x. Well, maybe you have to think about it in your head. I don't know. Well, oh, look, x is a common factor. Maybe you can do that. Okay, now what? Distribute back? Well, you're kind of stuck at this point. You have nothing you can do. You can't get one x value by itself. Or at least a set of x values by itself and 0 on this side. And I'll explain what good that ends up being. Okay, so you're stuck. Unless you do proper factoring. Okay, where you can use something called the zero product property. So we'll talk about that. There are 3 ways to express x as a first degree term to solve for it. One is by factoring. So let's do that example again. And let's factor this properly, where you get x plus 8 times x minus 4 equals 0. Okay, the zero product property states that if you have a product of 2 values and it's equal to 0, then it is impossible for one of these values to not be equal to 0. In other words, you cannot multiply 2 non-zero numbers and get 0 out. That would be impossible. Therefore, if I were to call this zero product property, I am multiplying this quantity x plus 8 by this quantity x minus 4. And if this is equal to 0, then that means either this guy must be 0, let's call this your A, or this guy must be 0, let's call it your B. That's the only possible way that you can get 0 out of this. Now the difference between this scenario and the scenario where I factored this out like this, I think it was x plus 4. The difference between these two is there is no such thing called the 32 product property, where if this times this equals 32, then either this equals 32 or this equals 32. No, you have to find something else more specific than that. In this case, for 0, one of these must be 0. So either x plus 8 equals 0, or x minus 4 equals 0. And if x plus 8 equals 0, then x would be equal to negative 8. And if x minus 4 equals 0, then x would be equal to 4. So here are 2 solutions here. And remember how we said that there are instances where this comes up where you have 2 solutions. Okay. Another way is by completing the square. And I think we're going to run into problems where we do completing the square. So I'm going to try and avoid that one here. But completing the square, it's best used when a single square has an even-numbered linear term. And I think I'll talk about that as we get into it. This is an excellent method to putting an equation into vertex form. So there's another way to do it if we can break this down into what's called a perfect square trinomial. That way we can make it factorable and we can get it into this form. This way you have a single x variable for which you can solve. Okay. And the final one's by quadratic formula. And if you're in my class, then you learned how to get to quadratic formula from here by completing the square and doing a bunch of other stuff involving fractions and kind of sticking consistent, making sure you know how to get to here. But the quadratic formula says if you have a quadratic equation, you may apply this right here. Okay? And this is the direct set of values for x where you can get your x-intercepts, basically. Here's your discriminant, b squared minus 4ac. Now this value right here tells you exactly how many solutions you'll have. Because take a look, this is the guy that's inside the square root. Discriminant is a word that kind of sounds like discriminate. Discriminant is a way of saying, I will discriminate against certain kinds of values. For instance, it's very generous toward positive values because you can take the square root of a positive number and get an answer out. And when you do, you may either add or subtract that value. So when you add or subtract a positive value, you're going to be looking at two different solutions. Let's do that example here really quickly. Just by taking the discriminant. If I do b squared minus 4ac, and your a value is 1, your b value is 4, and your c is negative 32, I will do 4 squared minus 4 times a times c. That's 16 plus 128, which is 144. Now 144 is a positive number, and the square root of 144, by the way, is 12. So when you plug this information in, you're going to add 12 in one iteration, and you're going to subtract 12 in the other. So that'll give you two different solutions. Okay. If your discriminant was 0, you'd only get one real solution. Because what would happen here, you do negative b plus or minus the square root of 0 over 2a, whatever your b and a are. Now the square root of 0 is 0, plus 0 is just that number, minus 0 is just that number. So your x value is just negative b over 2a. And this makes sense with what we've been talking about with vertex before. If there's only one real solution, that means that your vertex is your x-intercept. We already talked about that on one of the first slides. So your vertex would be negative b over 2a, kind of sounds right. This is where that number kind of comes from. Or by using calculus, but we're going to avoid that method. And finally, negative numbers give you 0 real solutions. Now next week we'll start talking about imaginary solutions, but if you get a negative discriminant, you try and take the square root. Let's say you get the square root of negative 20. Well, there's no real answer to that. Can't take the square root of a negative number and get a real solution for that. So there is no real solution for that. And again, no real solution. All that means is your graph never crosses the x-axis at all. Okay, ready to go? I want to do some word problems now. Or some word problems. I'm going to do some real problems with you. Let's breeze through this now that we've kind of talked about everything. This is just going to go 1 through 8. This chapter was focused on quadratic equations. Let's write an example of any quadratic equation. All right, I'll give you one. Y equals 2x squared minus 6x plus 9. Good enough? I'll give you another quadratic equation. Let's do in vertex form. Not this one. Let's do y equals 3. Let's do negative 3 times x plus 1 quantity squared minus 12. Okay. Cool. Sketch its general shape. I think they just mean sketch the general shape of any quadratic if it has no real roots. So remember what that means. We saw a sketch of this in the very beginning. Never crosses the x-axis. It may, and by the way, must cross the y-axis at some point, even if it's not visible, but boom, never hits the x-axis. Never crosses. Okay, how do you find zeros? Remember what zeros are. They're also called roots. They're also called solutions. One way to find zeros is to set your y value equal to 0. So if you have a polynomial, you'll set your y value equal to 0, and boom, you do any factoring or whatever you have to do there. Well, you do that, you either, like I said, factor, complete, square, or use quadratic formula. Another way to do it, really, is if you want to graph it, then find out where it crosses your x-axis. The only issue with this is it doesn't always cross in a clean place. Like it might cross at an irrational number, in which case that's probably not the best method to do. But at least you can have a good indicator of where it should have crossed. Okay, and what does discriminant tell you? Well, the discriminant tells you two things. First of all, it tells you how many solutions. How many real and imaginary, although we're not talking about imaginary numbers yet, solutions there are. It also tells you how many times, like as a result, it tells you how many times your graph crosses your x-axis. Sorry for the handwriting, kind of scribbling through that. Number 2, answer the questions using the graph provided. Okay, where's the vertex? I'm looking at negative 2, 3. Again, there is the vertex. Where's A? A is just another point on your graph, and it'll be a nice point to take care of here. 2, negative 2. Using the line of symmetry, or we called it the axis of symmetry before, okay, find the coordinates of point B that correlates to A. We've called these corresponding points in the past. If you remember that, it's basically if you reflect across your axis of symmetry. I didn't really talk about that in my notes. I do apologize for that. But if I want a point B right here, I'm going to look at point A, and I'm going to reflect it across here. This is my point B. It's the one where it's important when you do your own graphs, and I believe the next problem does have us graph. It's important that when you graph, you know that you don't have to look at both ways. You just have to look at one way and then reflect points across, because these parabolas are symmetrical, which means it's 1, 2, 3, 4 units across this way, just like it's 1, 2, 3, 4 units across that way. The point that corresponds to A is negative 1, negative 2, 3, 4, 5, negative 6, comma, negative 2, which makes sense. This should be the same height as A right here. Okay, where's the line of symmetry? Now, the line of symmetry is an equation. Okay? X equals negative 2. It will be the same place. Like, remember when I said x equals h for your vertex hk? In this case, my h is negative 2. So that is my line of symmetry. My domain is the set of x values which still reveal a y value. And in this case, there is no restriction on my domain. For any parabola, unless they tell you domain restriction, you'll always get all real numbers. Your range is a little unique, though, because as you can see, there's a point at which your parabola stops going up, or in another case like this, your parabola stops going down. And that is the height at its vertex right there. So you can see that your y values go as high up as 3, and then they don't go any higher. They start at, or if you think about it this way, they start from the vertex and go down. So it starts at 3 and goes lower. So y can be everything 3 or less than. Okay, and finally, what is the equation? I'm going to do this in 2 different ways. I'll do it in the way that I talked about earlier when you kind of plug in your values, and then I'll do it by working through a set of points that I know. Okay? First way here is by looking at vertex form. The reason I use vertex form is because I'm given 4 of the 5 points. Technically, 5 of the 6. Oh, 5 of the 6. I'm technically given multiple sets of points that I can use, but I'll use my a value because they gave it to us. How nice of them. Okay, now this is an xy value that is somewhere just on the graph. So if this is a solution to your graph, you can insert these values in. I can insert a negative 2 for y. I need to find my a value. That's my stretch factor. I have a 2 for x. I have negative 2 for h. So this is 2 minus negative 2. Be careful with that. And this is plus your k value, which is 3. So negative 2 equals a times 2 minus negative 2 is 4. That's 4 squared plus 3. Let me subtract 3 while I'm at it, and I'll get negative 5 over here equals 16 times a. So a equals negative 5 over 16. Ooh, that is a very difficult problem to work with as far as what's going on there when I said I wanted to do it a different way. The other way I would have done this problem is by applying my stretch factor as I know it. For instance, if this is a value that I know, I can go over from my vertex. I can go 1, 2, 3, 4 over, and I can go down 1, 2, 3, 4, 5. Now normally, when I go over 4, remember, normally, when I go over 4, I would go up 16. Now, I know that I'm going down, so I know that my stretch factor is negative. So let's take a look at some of these guys right here instead. Over 1, down 1, over 2, down 4. Now, this time I'm not going down 16. I'm going down 5. And 16 times 5 over 16 equals negative 5. So I'm going down, I should have just called this plus, because I want to multiply this by negative 5 over 16. I'm going down this factor of 16 instead. This is a weirder example. I do understand that. Normally you come up with an example that's a lot simpler to work with. But this becomes your stretch factor here, your a value. So you could have done it that way as well. And like I said, yeah, that wasn't the easiest one to work with to talk about that problem. Okay, number 3, rewrite y equals 2x squared plus 8x plus 5 in vertex form. Then we'll do number 4. I didn't see that over there. And then graph it. Okay, before I do that, I actually want to graph one point that I know, which is my y-intercept. My y-intercept is my value of y when x equals 0. You plug in 0 for x, these go out of the way, all that's left is that 5. So that's one point that I know. I also know my stretch factor is positive, so I know that it's going to be going upward. Okay, vertex form. By vertex form, if you recall what I said before, is it's good to complete the square. The reason for this is because in vertex form, you have what is called a perfect square trinomial. So I'm going to rewrite this equation. I'm going to practice completing the square. And I didn't really talk about completing the square too much, so let's give a little bit of a talk about it. I don't have much time to really get too into detail about it, but basically you need to create, well, you need to create perfect squares. You need to create what's called a perfect square trinomial. Now, if I have two x squared values, I can't create a perfect square out of two x squared values because your x's are unknown. So you need to factor out that 2 from here, and you need to just create one square that you want to complete, and you're going to complete them twice. This 5 is in the way. It has nothing to do with the squares that I'm going to complete. So I'm going to factor the 2 out of my x squared and my 8x values, and I'm left with that. Now this 5 is going to get way out of the way here, because it has nothing to do with the square that I'm going to complete inside here. Okay. Now by completing the square, all that means is there's a value that I can add here that will make this guy factorable. That'll make this guy a perfect square trinomial so that it'll be factorable as a perfect square. Now, whatever I add into here, I have to subtract out of here. Okay. Now, if you recall my example or my thing that I saw before, that I wrote before, if I have any perfect square trinomial, it tends to look like this, where your 2b value is the same as your linear coefficient, and your b squared value is the same as your constant term. So if I want to get from 2b to b squared, I have to divide this number by 2 to get b, and then I have to square it to get b squared. So let's take this example here, where my 2b value is equivalent to 4. My b value, therefore, is 2 if I divide it by 2, and my b squared value is 4, because 2 squared is 4. So this is x squared plus 4x plus 4. Now remember, whatever I add over here, I have to make sure I subtract over here to keep an equation balanced. But I didn't just add 4. Remember, if I distribute this 2 into here, this will be 2 times 4. So over here, I'm not just multiplying by 4. I'm not just subtracting 4, I'm subtracting 2 times 4. And 2 times 4 is 8. So what I'm going to have here, the whole idea for this is, again, in normal cases when you want to solve for something, you need to make this a perfect square trinomial so it's factorable into one x value. X squared plus 4x plus 4 factors into x plus 2 quantity squared. And this is 5 minus 8. 5 minus 8 is 3. So your final solution is y equals 2 times x plus 2 quantity squared minus 3. Let me write it here one more time. Remember, it is an equation. That's what we get. Okay. How do we graph that? Well, let's look at the vertex. That would be at -2, -3. Now let's go, let's start talking about that stretch factor stuff again. If I have a stretch factor of 2, remember, the general scenario for a parent graph, if the stretch factor is 1, you go over 1, you'd go up 1. From your vertex, you'd also go over 2 and up 4. But this is not a stretch factor of 1, it's a stretch factor of 2. Instead of going over 1 up 1, I'll go over 1 up 2, because that number is 2 times 1. I'm taking this 2, and I'm multiplying it by 1. Instead of going over 2 up 4, I'm going to go over 2 up 8. Because that number is 2 times 4. Okay, 2 times 2 squared. Now this value was already up here. It's good that we had this because that confirms that that was a valid point. How about on the other side? We can reflect across our axis of symmetry. So if you had an axis of symmetry right here and said, okay, points reflect across here, you don't have to count anymore. You can just reflect straight across, like here and here. Now I know this graph is not going to look good, but let's go for it. Boom. And that should not look so V-shaped. That should look a lot more U-shaped. We'll try that again. Boom. Now it just looks terrible. But anyway, your graph, it goes upward. It's going it's going taller than a stretch factor of 1, and we're on our way. Okay, number 4. Solve x times x minus 5 equals x plus 8. Let's try this a few different ways, whatever works best. I'm going to distribute. So to solve for this, you need to, this is a good reason to distribute. You want to combine like terms wherever you can. So let's subtract x and subtract 8. You'll get x squared minus 6x minus 8 equals 0. Now your first step might be to look at this and say, can I get a common can I get two numbers that multiply to negative 8 and add to negative 6? And you try things like, oh, negative 4, negative 2, stuff like that. But it's like, well, that multiplies to positive 8. So this isn't factorable. We're already knowing we're looking at something not factorable. So we have to ditch that plan. Now you say, okay, I'll try this two different ways. Let's try completing the square, and let's try quadratic formula. Both of them should work when all else fails. Completing the square. Get this negative 8 out of the way. In fact, I'm going to add it back over to the other side. This has nothing to do with the square that I'm going to complete using this information right here. What I want to do is add a value, and whatever value I add to the left side of the equation, to keep the equation balanced, I also need to add to the right side of the equation. Now before, when I subtracted, that was because I was on the same side of the equation. When I added a 4, I subtracted my 2 times 4 because I was on the right side of the equation. If I add 8, I must subtract 8 to cancel out. Here, I'm on opposite sides of the equation, so whatever I add on one, I must add to the other. Okay, if my 2b value is negative 6, my b value is negative 3, therefore my b squared value is 9. That'll give me a perfect squared trinomial here. Whatever I add on one side, I must add on the other. Okay? This factors into x minus 3 quantity squared, and this number here is 17. Now to solve for x, what you have to do is take the square root of both sides. Okay? Take the square root of this side, that'll cancel out my square value, so I can start to solve for x. Remember, the rest of this at this point is just algebra. X minus 3 equals plus or minus the square root of 17. And you add 3, you get x equals 3 plus or minus the square root of 17. Now this final answer is good enough. You don't really want to punch this in the calculator and see what decimal you get, unless you're graphing and you just want to make sure that you're kind of around the general area that you want it to be at. Okay. Another way to solve for this, and I'm actually going to erase this here, is quadratic formula. And I want to confirm, remember x equals 3 plus or minus root 17. Remember that answer. Okay. Quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac over 2a, can give you your exact answers as well. But let's first work toward the discriminant. If you use your discriminant, you don't have to rewrite all this b squared minus 4ac stuff inside your root every time. Like b is negative 6, and your a is 1, your c is negative 8. So it's 36 plus 32, which is 68. Okay? So that's my discriminant value. That is the value that will go inside my square root when I do this problem here. So now I'm going to get x equals negative b. Now my b already was negative, so this will give me a positive 6. I'll just write the opposite of negative 6. Plus or minus the square root of 68 all over 2 times 1. That's 2a. So x equals 6 plus or minus the square root of 68 over 2. So you sit there and you're like, well, I'm done. The problem is, remember, we should get the same answer as we got over here. So you're like, what's different? Well, what's different is we didn't simplify a radical. You see the square root of 68 right here? This is factorable. I'm sorry, you can simplify this. A perfect square exists inside here. And you have to kind of determine which one. So you'd say, or what the biggest one is maybe. Is it 4, 9, 16, 25, 36, etc.? Well, I know it's not 36 and 25. 16, 32, no, not going to be that one. 9, oh no, 4. Okay, we can divide a 4 out of here. So I'm going to write off to the side here. We'll get square root of 68. That breaks down to square root of 4 times the square root of, oh, I don't know. What is it? Oh, is that 17? And square root of 17, which gives you 2 root 17. So I'm going to rewrite this equation down here as x equals 6 plus or minus 2 root 17 over 2. And you're still like, wait a second, this still isn't the same thing as 3 plus or minus root 17. I'm still not convinced. Well, you got a 2 in the denominator here, and it's dividing both by the 6 and the positive or negative 2 root 17. We can do some cancellations. Now, here's where you got to be careful. This is what I see a lot, and trust me, I've been teaching this enough where I've seen it a lot. Okay, I'm good. Again, be careful. You just divided 2 by 2. That's fine, but you can't just cancel this out. You have to make sure you're dividing the 6 by the 2 as well. So there are a few ways that you can accomplish this to be certain. One way is to factor a 2 out of the top. And what's left on the inside is 3 plus or minus 1 times the square root of 17, which is just the square root of 17. This is divided by 2. 2 over 2 is 1, so you're just left with x equals 3 plus or minus the square root of 17. Another way to do it, if you don't like that method, is you can separate this 2 into 2 different fractions here. So it's x equals 6 over 2 plus or minus 2 root 17 over 2. And now you can say, all right, 6 over 2 is 3. 2 over 2 is 1, so you get plus or minus the square root of 17. No matter what you do there, you still end up with the same response, or the same result as you got over here when you completed the square. Okay? Okay, solve by factoring quadratic formula or completing the square. This time I'll go through it a lot more quickly here. It's your choice as to what to do, but again, you can only solve by factoring if it's factorable. So I'm going to first take this over to this other side. Let's see if this is factorable. Negative 4, negative 3. Negative 4 and 1. Go to that. So it's x minus 4 times x plus 1 equals 0. And if that's the case there, now you're getting into something where you can apply the zero product property. If x minus 4 times x plus 1 equals 0, either x minus 4 equals 0 or x plus 1 equals 0. So in that case, either x equals 4 or x equals negative 1. I won't do this by completing the square and quadratic formula. I'll only do it if necessary. So let's check out these other ones. All right, part B, x squared equals 8x plus 16. I've distributed. Subtract x squared minus 8x minus 16 equals 0. Factorable? See, negative 16, no, negative, no, not negative 4, negative 4. Okay, not factorable. Let's do this one by completing the square. If the next one's not factorable, I'll do by quadratic. Well, 70, that's going to be a big number. Let's do quadratic formula for this one. First thing I want to do is my discriminant. B squared minus 4ac. So we'll get negative 8 squared minus 4ac. Looks like we get a big number anyway. I don't know what my fuss was about. 8 squared is 64. This number is also 64. So that gives you 128. Okay. Now when we get 128 here, that's what's going inside your square root. So maybe before I even begin doing this, because I know I'm going to take the square root of 128, maybe I say, let's simplify this first. Now we know 128 is 64 times 2. You can take a look right there. That's square root of 64 times square root of 2. Square root of 64 is 8, so we're left with 8 root 2. So when you do quadratic formula, you know that song that you would always sing to make sure that you remembered it? You don't really have to do that anymore, at least not that whole b squared minus 4ac part. You still need to know the opposite of b, so this is 8, plus or minus 8 root 2, the square root of b squared minus 4ac. That's what that guy came down to. All divided by 2 times 1, which is 2. So I've already broken this down. I didn't have to write this whole thing if I'm trying to follow too much of a protocol. Notice how bad that gets. And then you have to do that over and over and over again until you break it down to this part. Now at this step, you can either do one of two things. You can either factor out, now you could factor out an 8, but you just need to factor out enough so that you can cancel the 2 out, in which case I can factor out a 2. So if I factor out a 2, I'm left with 4 plus or minus 4 root 2, all over 2. 2's cancel, and then x equals 4 plus or minus 4 root 2. Okay? You may either do that, or you may separate this. So it says x equals 8 over 2 plus or minus 8 root 2 over 2. And then divide 8 over 2. And divide 8 over 2 right here. You get root 2. Same thing. Taking a look at the answer key actually, because the square was completed in it, I want to make sure that I do this problem that way as well, only so that you see why the answer that they got, or that is put there, is not the same as this. It is the same, just they didn't simplify the radical. Let's go ahead and try that a second way. I know it stretches out this actual thing, but you can always skip anything that you feel you got a handle of. So completing the square here, we'll do the same thing. X squared minus 8x minus 16 equals 0. But to complete the square, I want to get the 16 over to the other side. No good over here. I'm going to be adding anyway. So I need to add a number here that'll be added here. Remember, you take this number, divide it by 2, negative 4, and square it. That number is 16. 16's over here, then 16's over here. This factors to x minus 4, quantity squared, and we get 32 on this side. Okay. Take the square root of both sides, and you get x minus 4 equals plus or minus the square root of 32. Now remember, square root of 32 is factorable. That's the difference between the answer that you get here and the answer that you get here. We want to try and break down square root of 32 to the square root of 4, or excuse me, to 4 times the square root of 2. And how do we do that? Well, the square root of 32 is the square root of 16 times the square root of 2, and the square root of 16 is 4. So you're left with 4 root 2. So your final answer is x equals 4 plus or minus 4 root 2. So again, you still get the same solution no matter which way you approach it. Okay. And finally, the third problem, part C. This looks like it's factored for you. By and large, it kind of is, but it being factored is not going to help you in this scenario, because just like there's no such thing as the 32 product property, there's no such thing as the 70 product property. So I actually have to expand this again. This will be x squared plus 5x plus 2x. That gives you 7x plus 10 equals 70. So I can either complete the square, use quadratic formula. I think some people still need more complete the square practice. Even though it's going to give us fractions, it's either fractions or a huge number. And right now I'm not very huge number. I don't have a calculator, so I'm not very huge number happy. Okay. So I'm going to subtract the 10 over. And I want you to make sure that you know how fractions work when you do completing the square here. Anyway, so it's good practice. You get x squared plus 7x plus a number equals 60. That's 70 minus 10. Now here, let's check this out. If 2b equals 7, then b equals 7 halves. So b squared equals 7 squared over 2 squared. That's 49 over 4. So I add 49 over 4 on this side. So I'm going to add 49 over 4 on that side as well. Okay? Now, you're going to you're going to not like me for saying that this can also be solved by factoring. But I want you to see that you can do this problem by completing the square. Okay, so you get this breaks down to x plus 7 over 2, quantity squared. That equals 60 is 240 over 4. So this is 240 over 4 plus 49 over 4, which is 289 over 4. So x plus 7 over 2 squared equals 289 over 4. Take the square root of both sides. You'd think that this comes out strangely. It actually comes out great. Because the square root of 289 is 17. So x plus 7 over 2. Now this is also where you get to practice this idea right here. Square root of 289 over 4 is the square root of 289. By the way, this is plus or minus. Square root of 289 over the square root of 4. So that becomes plus or minus 17 over 2. So now, this can break into two equations. When I subtract this negative 7 halves, it's either x equals negative 7 halves plus 17 over 2, or x equals negative 7 halves minus 17 over 2. So that is either x equals 10 over 2, so x equals 5, or x equals negative 24 over 2, so x equals negative 12. All right, now we got full integer answers, so you start and sit and say, wait a second, we could have solved this by factoring. Well, yeah, you could have. Because what we had here was this step. I could have subtracted over this 70. I'll get x squared plus 7x minus 60 equals 0. This is why you always want to check and see if it factors first. However, there are times where it doesn't, and then you end up feeling like you wasted your time, so you want to decide which way you want to go about this. Negative 12 times 5 is negative 60. Negative 12 plus 5 is 7. I'm sorry, I did that wrong. 12 minus 5. So that's x plus 12 times x minus 5 equals 0. So x equals negative 12, or x equals 5. Just by zero product property, you can kind of get to that step afterward. And we get the same answer as we got before. Okay, feeling accomplished. We only got a few more problems left. Word problem. Let's see if a word problem can make sense with what we talked about before. Let's read the problem, discuss it, and see what we got. You are standing at the top of a 50-foot cliff. If I were to draw this, here's your cliff. Here's you. This guy's 50 feet. You throw a ball up in the air and watch it fall. Whee! The path that follows is given by this, where y is height and t is time. So don't assume that the ball necessarily went out this way. When you look at this parabola in this thing, it's not showing the distance it goes away from you. It's showing how much time has passed after you throw it. So assume, really, you probably just threw it straight up in the air and it went back down. But it goes to the bottom of the cliff. So here's your graph, or here's your path. We'll check out the graph kind of by looking at the vertex equation. In fact, let's do this a different way. I want you to look at negative b over 2a example, and I'll do completing the square, so you look at both. To get your vertex, you can do negative b over 2a for your x value, which is negative 48 over 2 times negative 16. That's negative 48 over negative 32, which is positive 3 over 2, or positive 1.5. There's 3 over 2. Now you get 3 over 2 for your x value, and your y value here, as you plug this in, is negative 16 times 3 over 2 squared plus 48 times 3 over 2. I really wish I had a calculator right now. Plus 50. Oh, the days I wish I had a calculator. Negative 16 times 9 over 4 plus 48 times 3 is 144. Now 144 over 2, look, that can simplify. I'm not going to leave that over 2 for much longer. Plus 50. In fact, a way I should have done this really, instead of negative 16 times 9, do negative 16 divided by 4. That's negative 4. Negative 4 times 9 is negative 36. 144 over 2 is 72. And there's 50. So y equals 122 minus 36, 160, 86. 86. So here's your vertex. It's positive 3 over 2, comma, 86. Now 3 over 2 is in time, so if you think about that, that's 1.5 seconds. After 1.5 seconds, the ball reaches its maximum height of 86 feet. So to answer the question that was being asked, when and where does it reach the maximum height? There it is, at your vertex. So let's go and just kind of look at a really cheap graph of this. Here's a graph. Here's after 1 second, 2 seconds. Here's 1.5 seconds right there. Here's you at 50 feet. Here's 86 feet. You throw this ball, it goes up. Now remember, it's not going outward, but as time goes by, it reaches its peak, and it keeps going down, 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 until eventually it hits the ground at some point as well. I'll just place that there. It's probably the next answer. When will it hit the ground? Oh, I'm sorry. 3 won't be its answer. That was stupid of me. It crosses through. Okay, when will it hit the ground here? And the answer is not 3. When will it hit the ground? Well, this is an x-intercept. So if this is an x-intercept, then this is a value for x when y is equal to 0. So what we're going to do is use this equation, or you can use this equation, y equals negative 16 times x minus 3 over 2, excuse me, squared plus 86. You can use either or, because this is we've already completed the square here. We might want to do it this way. You might not want to use quadratic formula here, and that might be very hard to factor. So I'll work with this equation and figure out when it hits. Now the thing is, you're going to get 2 solutions. Because if you think about this, this is a quadratic that hits the x-axis here and here. But this way, we don't count time negatively here, so we're just going to look at positive time and where it crosses. So when you get a negative answer, we're going to ignore it. We're only going to look at our positive answer. So I'm going to use that equation over here again. Let's write it down below. Y equals negative 16. Oh, by the way, it's not an x, it's a t. Y equals negative 16 times t. Did I put plus or minus 3 over 2? Minus 3 over 2. Quantity squared plus 86. We're trying to find this out when y is equal to 0. So let's solve for t. Let's get it by itself. Subtract 86. Negative 86 equals negative 16 times t minus 3 over 2 quantity squared. Divide by negative 16. And we get, oh gosh, that's not a pure number. 86 over 16. I want to make sure that my 86 was right before I continue this. Make sure it shouldn't have been 96. 122 minus 36, 160. Yeah, that should be 86. So 86 over 16 equals t minus 3 over 2 quantity squared. I might as well take the square root before I simplify. Well, I think I can simplify. Oh, no, I can't. Let's take the square root. Square root of 86 over, remember, square root of 16 is 4, equals this guy. T minus 3 over 2. Square root of 86. Let's see if this can break down to anything in particular. Okay. I can break that down to 2 and 43. Now, if you can break it down to that and you just end up with primes, that's all you're good with. Square root of 86. Not much you can do there. That is just an unfortunate number, and there's nothing else we can do about it. So let's add 3 over 2. So if we add 3 over 2, this t equals 3. Oh, by the way, this is plus or minus. Well, it's plus or minus, but we're not going to subtract this, right? We're only going to look at the positive answer. So this will be plus root 86 over 4. Now, I want to get a common denominator if possible, so I'm going to multiply this guy by 2 over 2. So I'll get t equals 6 over 4 plus root 86 over 4. So that's 6 plus root 86 over 4, like that. Okay. Now, what is that number? You can input that in the calculator. And I'm taking a look at the answer key here. Although they use different stuff for their quadratic, they used quadratic equation to do this. Looks like they got 3.818 seconds. So I'm guessing this also gives you 3.818. And that's how long it takes for the ball to hit the ground again. I'm assuming your test problems aren't going to be so finicky with it, like very, square root of 86, tough to work with. Okay, find the quadratic that passes through the points negative 1, 11, 1, negative 1, and 3, 3. Now, this wasn't in your notes, so to speak. This wasn't a problem that whatever, but this is still an example where you can plug in values knowing that this is a quadratic. You know that quadratics can come in standard form, like this. Okay. When they come into standard form like this, you can plug in, remember these are x, y values. We can create a system of 3 equations and 3 unknowns. And we can make this happen, boys and girls. So I can plug in 11, negative 1, and 3 for y. And I'll get 3 different equations. When y is 11, x is negative 1. So this is a times negative 1 squared plus b times negative 1 plus c. This is a times 1 squared plus b times 1 plus c. And this is a times 3 squared plus b times 3 plus c. If I clean this up, I'll create the following system. Let's use happy blue. Oh no, that's royal blue. I got to get rid of that. Go Giants. Go Orange Giants. That'll be negative 1 squared is 1, so I get a minus b plus c equals 11. 1 squared is a, or is 1, so a plus b plus c equals negative 1. And 9a plus 3b plus c equals 3. The thing that I always like about these systems is that you can always eliminate your c's if you'd like. You just have to make some values negative instead. So let's say that I make the second equation negative, and I can eliminate c with the first and second equation and the second and third equation. So this will be negative a minus b minus c equals positive 1. So I'm going to add down these guys right here. Okay, and I will get, and look, the a's eliminate as well. I'll get negative 2b equals 12. So b is negative 6, which is kind of nice. And again, it's kind of interesting. My aim here was to create a system of 2 equations, and I still have to do it because even if I got 6 for b, I still have to plug it into one of these. But it's nice that I kind of just got something where now I can just substitute. I don't have to go much further for this here. So let's combine these two together. Okay, and I'll get 8a plus 2b equals 4. Now remember, b equals negative 6, so I can plug that in here. So 8a plus 2 times negative 6. It's funny how my b's always become 6's because they always look alike. I've been noticing that as I've been doing this today. 8a minus 12 equals 4. 8a equals, what is that, 16? 16, so a is 2. Bada boom, bada beam. And finally, coup de grace, plug it into one of these equations. Just be careful, that's a negative. See, those look like the same thing. This is a negative 6, and that's a b. But I got to plug in negative 6 for b, so I'm going to subtract a negative 6. So 2 minus negative 6, that's not a 6. We'll set it again. Plus c equals 11. 2 minus a negative 6 is 8. And c equals 3. So I have an ordered triple here that's 2. Well, it's not a triple. It's not a location. These are coefficients. A is 2, b is negative 6, and c is 3. So if you look at your original polynomial function here, these are the coefficients that pass through those 3 points. So I plug in 2 for a. I'll get y equals 2x squared. Negative 6 for b, 6, and 3 for c. This is my final equation. Okay, and I'm satisfied with that. In other words, if I were to graph this or anything else, this is the graph that passes through these 3 points. And it's the only parabola that can pass through those 3 points. It's unique to it. That's why we only got one equation. Okay, last set of problems, number 8. How many solutions will each equation have? Explain how you know. There are a few ways you can do this. I'm going to go just by the discriminant method. You could graph this. You have to be careful and make sure your graphs are right, though. Basically, if b squared minus 4ac is greater than 0, if it's positive, I have 2 real solutions. If it's equal to 0, I have 1 real solution. And if it's less than 0, I have 0 real solutions. So I'm going to plug in my a, b, and c values here. If this is equal to 0, then I'm looking at b being negative 3. So b squared minus 4ac. So that's 9. Minus 4 times negative 5 is plus 20, which is 29. Does my value matter for this? No, I'm not solving for it. I'm just trying to find out how many solutions there are. There are 2 real solutions here. Okay. Let's divide this guy right here. Okay, let's look at part B. I have this guy here equal to 0. Okay. So I got b squared minus 4ac. Bigger numbers this time. That's 144 minus 4 times 4 is 16. 16 times 9 is actually 144. So 144 minus 144 equals 0. If it's 0, that's 1 real solution. And finally, okay, this guy right here, if you want to use your discriminant, you have to put this in standard form. So I'm going to distribute here. I got x squared plus 3x equals 5x minus 50. I'm going to subtract these guys over. I need these all on one side of the equation. Plus 50 equals 0. All right. Now, discriminant. B squared minus 4ac. That is 4 minus 200, which is a negative number. Negative 196. You don't really need the answer as badly as you need to know that it's negative. This has no real solutions. Okay. Anyway, probably something that I should have mentioned in the beginning here. You know that you have the answer key for this guy. I talked through these as I went, though, so maybe something that you heard clicked for you for this. But these are all of the problems that we did. I think this one took longer than 90 minutes, which our normal problems were, because these notes were a little more extensive. I did do some example problems along the way, like you saw, and there were some pauses in between that I had to go through. But assuming this stuff makes sense, you should be pretty okay for your exam there. Some of the stuff, this was a pretty important, well, all of them are pretty important pages, but these pages are kind of ones that you really want to reference and see that you can make use of. Okay? So I'm going to sign off. If you do have any other questions, please let me know. Ask in any sort of way that you need to, whether it's email, text, whatever it is, school loop, and I'll get back to you. All right? But best of luck to y'all.